Hello and welcome to the Algorists. In this video, we will talk about articulation points in an undirected graph, and we will also look at its code as to how to implement it. So let's get started. So there are several videos and tutorials out there in the internet, and most of them I have seen just go through the algorithm of how to compute the articulation points without giving any explanation as to why the algorithm actually works. So the main motivation behind making this video is to actually find out the rationale behind the algorithm as to why the algorithm actually works and why the algorithm is actually able to find out the articulation points. So we will start with a clean slate and we will try to figure out the algorithms ourselves using different logic and different observations. If you are preparing for a coding technical interview where you would know that you might be asked coding questions based on algorithms and data structures, or if you are interested in and preparing for competitive programming, then knowing the ins and outs of articulation points, bridges, and bi-connected components in an undirected graph is really important. Problems based on articulation points will seem very easy if you already know the concepts of articulation points really well. But the same problem will become very tricky to solve if you don't know the concept well. So let's see what articulation point actually is. For that, we need an undirected graph. So it is very important to note that articulation point is present only in undirected graphs. This concept does not apply to the directed graph. In directed graph, we would see something similar when we would discuss about strongly connected components. So to discuss about articulation points, let's get started by taking an undirected graph. So we have taken an undirected graph here. Now I would like to bring your attention to three nodes here. That is the node 5, 6, and 2. What do you think would happen if we remove any of these three nodes? So if we remove, say, 6, now we would see that we have two disconnected graph. So this undirected graph was connected. Removal of the node 6 disconnected the graph. So let's see what happens if we disconnect, say, 5. Then again we would have two disconnected components. Now let's talk about the node 2. If we disconnect the node 2, now we actually have again two disconnected components. This one component with just one node, and the rest of the disconnected graph. So these three nodes we would call articulation points. And in this video we will focus on how we can find out the articulation points in a given undirected graph. So you can see that articulation points is in a lot of places in our real world scenarios. Like the first thing that comes to my mind is in computer network. So when we study about computer network, like some of the first few things that we learn about, which are very crucial in networks, is the single point of failure. So these articulation points are nothing but single points of failure. So whenever we have any network, computer network, or any dependent dependency graph, it is very important to figure out if we have a single point of failure, or if we try to extrapolate in different other scenarios, then to say in more generalized form, these articulation points may represent any choking point or any bottleneck. Another example would be in our everyday life, we use GPS maps, and we know the maps are fundamentally um, implemented using graphs. If we have routes, and if we see that if one particular intersection gets blocked, and if that hinders people from going from place A to place B, then that intersection is acting as single point of failure in the connection between place A and place B. So that is also an articulation point in a given graph. So now let's focus on how we can actually find out the articulation points. For that, we need to make some observations that will help us to actually come up with an algorithm. First of all, um, when we remove node 6, node 7 and 3 becomes disconnected from the rest of the graph. Have you thought why that actually happens? Like, what could have prevented that? It would have been prevented if from either of 7 or 3 we had any other edge that would have connected to any of the nodes in the other component that we get after the removal of the articulation points. So if we have a spanning tree for that undirected graph, and why we need spanning tree, because we just need all the nodes, and all the nodes should be connected to each other through any path. So we can remove all the redundant connections, and we can just have the spanning tree. So we can do a DFS, and we can have a DFS spanning tree. So for this we can get a DFS spanning tree as this. And if we look at this DFS spanning tree from top to bottom, then we would see that 7 and 3 would not have been disconnected if either 7 would have an edge which goes to any of the nodes that was discovered while doing the depth first search while forming the spanning tree. So if we would have a node from 7 to any of the nodes that was discovered before the articulation point was discovered. Um, so if we have, so this edge now you know is nothing but a back edge because it goes to one of its ancestors in the DFS spanning tree. So now let's say if we remove 6, we see that the rest of the graph is still connected. And same goes for if we had a back edge from 3 to any of its ancestors. So this is a very important observation that if we have a back edge from any of the descendants of the current node that we are visiting while doing DFS, then that node cannot be an articulation point. What I mean is that, say, we are at node with 6 now, so 6 is the current node, and we are doing DFS on 6, and from there we will be doing DFS on its adjacent nodes, and then the rest of the descendants. So here 7 and 6 are the descendants of 6. So if we see that any of those descendants have a back edge, then 6 cannot be an articulation point. But in the given graph, either 7 or 3 does not have a back edge. That is why 6 becomes an articulation point. Um, so how can we represent using some data structures? So as we do the depth first search, say we started the depth first search from 1, so we visited 1 first. So we need to keep discovery time for every nodes as we are visiting them. So the discovery time of node 1 is 1 because that is the first node we discovered. From there, in our DFS, we discovered the node 2 second, so we put a discovery time of 2. For 4, we put discovery time of 3. For 5, we put discovery time of 4. For 6, we put 5. For 7, we put 6. And for 3, we put 7. So from here, at any point of time, whichever is the current node, we will have to see if any of its descendants connect to a node which has already been discovered. So while I'm at 6, 1, 2, 4, and 5 have already been discovered. So if any of the descendants of node 6 has a back edge to any of the nodes which have already been discovered, then we know that the current node, which is the node 6, is not an articulation point, which means we need to keep track of the earliest node that any node is connected to. So for 7 and 3, we need to keep the earliest node that they are connected to. So if they had one back edge to say 4, then the earliest node would have been the node 4. But as we can see from the given graph, the earliest node that 3 is connected to is actually the node 6, because we see that node 3 is directly connected to node 6. And actually in this DFS spanning tree, that is a back edge that we have from 3 to its ancestor 6. So we got one formulation here. So if we are so for the current node, if none of its descendants in DFS spanning tree has a connection to a node that is discovered before the current node, then the current node is an articulation point. Okay, so now comes that how we the second most important thing is how would we compute the earliest discovered node that is really reachable from a node. Say like when we are at 7, how would we compute that what is the earliest discovered node that is really reachable from 7 through some back edge. Now while discussing this, it is very important to note that while computing the earliest discovered node reachable from a descendant, we should take care that we are computing that by using only one back edge, and we should not have more than one back edges in the path that goes back to one of the earliest discovered nodes. Ask why? Okay, so let's take the node 3 for an example. The earliest node, earliest discovered node reachable from 3 by using one back edge is 6. Now if we are using say two back edges, then we can as well say that the earliest discovered node reachable from 3 is 5, because 6 is connected to 5 and we have a back edge from 6 to 5. So if we use the back edge from 3 to 6 and then 6 to 5, we can say that even 5 is reachable from 3, or we can even go on extending the same concept and using the back edge from 5 to 4, we can even say 4 or maybe even 2 and 1. Now if so, what is the problem when if we use more than one back edges? The problem is that the nodes which are connecting to those back edges, if we remove one of those nodes, then this descendant node, which is 3 in our example, becomes disconnected again. So one of those nodes which are connecting the back edges, one or more of those nodes are actually the articulation points. So like here we already know that 6 is the articulation point, and if we are taking more than one back edges from 3, then we are going through the articulation point. So it is very important that while computing the earliest discovered node reachable, we should have no more than one back edge. And when I say the earliest discovered back edge reachable, by reachable I mean that it is reachable through one of its um, descendants and using one back edge. So let me write down, and by forward I mean the descendants in the DFS spanning tree path. So for 6, the descendants are only in the forward direction. So 7 and 3. So for any node, while computing the earliest reachable earliest discovered reachable node, we should go forward to the descendants, and from any descendant we can have one back edge. So let's write down the second observation we had, and that is um, while computing earliest discovered node reachable from a node, we can have only one back edge. So these two are the constraints or observations, we can say, that we made till now, that we need to use while designing our algorithms as to how to find the articulation points. So now let's figure out how we can compute the earliest discovered nodes reachable from other reachable from any node in the graph. So for that, as we already discussed, we need to keep track of the discovery time and we need to keep track of the earliest discovered node reachable. And this we need to do for all the nodes we have. So let's see how we would actually do it. So as I mentioned, the first thing we need to do is construct the DFS spanning tree. And as we know, we can start the DFS spanning tree from any node in the graph. So let's not start with the node 1. Let's start with, say, node 2. So we started with the node 2. We put the discovery time of node 2 as 1, and since node 2 is the starting node of the depth first search, before that let me remove this backage because we don't have this backage. Yeah, so since node 2 is the starting node of the DFS search, so this is discovered first, so no other node is discovered before discovering the node 2. So definitely the earliest discovered node reachable from 2 is 2. So I will put the discovery time here. So we will actually put the not the node ID here. We would put the discovery time here, and from the discovery time we would know that which node that is. From 2 we can either go to 1 or 4. So let's go to 4. So we are at 4. The discovery time would be 2, and right now we don't know that what would be the final earliest discovered node reachable from 4. So we put the so we initialize it with the discovery time of the same node, and then we will go on improving this as we compute its descendants and all its adjacent nodes. So from 4 we go to 5. I put 3 for both discovery time, and we also the earliest discovered node really reachable. From 5 we go to 6, we put 4. Then from 6, say we can go either to 7 or 3. Say let's say we went to 3, so let's put 5 here, and from there we went to 7, so we put 5 in 7. So from say 7 we see that 7 has two adjacent nodes, 3 and 6, and both of them are visited, so we don't have to do any more DFS on that, because if we do that, then it will go into an infinite loop. um, so now that we know that we have no adjacent nodes that we need to do a DFS on, we would compute the earliest discovered node reachable from cell 7. So it is important to note that we will be computing the earliest discovered node reachable at the time of backtracking, um, because when we are backtracking, at that time we have information about all the descendant nodes and all the adjacent nodes from for the node from where we are backtracking. So say when we are backtracking from 7, we have already computed the earliest discovered node reachable for its descendants, and it has no descendants. So what I'm trying to say is we need to compute the earliest discovered node reachable when we are backtracking. That is why we did not see that we did not check if we were getting a better value for the earliest discovered node reachable till now, because we were not backtracking. So now that I'm backtracking from 7, so let's see, we have two adjacent nodes, and we see that both of them are visited. So if if a node, an adjacent node, is visited, that means that is one of its ancestors, and we know that we cannot take more than one back edge. So we know that that any or so then we will iterate over all the all the adjacent nodes which are ancestors, and then we will see that which one of them has the lowest discovery time, and we are iterating only on the ancestors here because all its adjacent nodes are ancestors for 7. So I see that the discovery time for 3 is 5, and discovery time of 6 is 4. So the minimum of 5 and 4 is 4. So the lowest so the earliest discovered node reachable from 7 is 4, and it is very important to understand that what we are doing here. So in this spanning tree, we started discovering nodes from 2, and then we went on discovering 4, 5, 6, 3, and 7. And for 7 we are saying that what is the earliest discovered node we can reach from 7, and we can use only one back edge, and the reason for that we have already discovered, because if we have more than one back edge, then one or more of the nodes connecting the back edges can actually be the articulation point. So from 7 I know I can reach to 3 through its adjacent node, and we know that from 7 we can also reach to 6 using the adjacent node, but 6 happens to come before 3 in the DFS spanning tree. That is why we know that the 6 is the earliest discovered node reachable from 7 using just one spanning tree. That is why in earliest discovered node reachable we put 4 for 7, because 4 is the discovery time for the node 6. Um, so now we backtrack from 7 to 3. Now that we are at 3, now that we are at 3, we would see that what is the earliest discovered node. We can go from 3 using its adjacent nodes. So the earliest discovered node uh, which is visible from any of its adjacent nodes will also be visible from the current node as well, which is 3, as long as we are not using more than one back edge. So the adjacent nodes are 7 and 6. For 7, the earliest reachable node is 4, and for 6, since 6 is the ancestor of 3, we don't even look at the earliest reachable node from 6. We look at the discovery time of 6, because the earliest discovered node reachable from 6 may require more than one back edge, and we already have one back edge from 3 to 6, since 6 is its parent. So we take the minimum of the lowest we take the minimum of the earliest discovered node reachable from 7 and the discovery time of 6. So the discovery time of 6 is 4, and the earliest discovered node reachable from 7 is also 4. So for 3, we take the minimum of the current earliest discovered node reachable and the minimum we got from all its adjacent nodes. So the minimum of 5 and 4 is 4. So we update the earliest discovered node reachable from 3 to be 4. Now we are backtracking from 3 to 6. 6 has 3 adjacent nodes, out of which one is its parent, the node 5. So we will take the minimum of the discovery time of 5 and earliest discovered node reachable from 7 and 3. So earliest discovered node reachable from 7 is 4, 3 is 4, and the discovery time of 5 is 3. So for 6, we have 4 as the earliest discovered node reachable. We make that 3. And if you look at the diagram now, that actually makes sense, because using just one back edge, node 6 is only can reach only to its ancestor 5 and not to any other ancestors. If it reaches to any other ancestors, then it would need more than one back edge. Now we backtrack from 6 to 5. 5 has 1, 2, and 3 adjacent edges. And out of the 3 adjacent nodes, which are 2, 4, and 6, 2 and 4 happens to be its ancestors. So I will take the minimum of the discovery time of 4, discovery time of 2, and the lowest the earliest discovered node reachable from 6. The earliest discovered node reachable from 6 is 3, discovery time of 2 is 1, discovery time of 4 is 2. So the minimum is 1. So for 5, I would put the the earliest discovered node reachable is the node with discovery time 1. And if you also look at the given undirected graph, um, you can actually reach the node 2 from node 5 using just one back edge. So using one back edge, 2 is indeed the earliest discovered node from 5. Now we backtrack to 4. For 4 we have two adjacent edges connecting to 2 and 5, out of which 2 happens to be its parent. So we will take the minimum of the discovery time of 2, which is 1, and the earliest discovered node reachable from 5, which is also 1. So we will and the current earliest discovered node reachable from 4 is 2, so the minimum of 1 and 2 is 1. So we update the earliest discovered node reachable to be 1. Now we backtrack to 2. 2 has uh, 3 adjacent nodes, 5, 4, and 1, out of which one is not even on the call stack, because we because we haven't visited 1 yet. So we have only um, 4 and 5, like 5. So when we backtrack to 2, we actually finish doing the DFS on 2. So to finish doing the DFS on 2, we actually need to visit the other adjacent node, which is 1, which is not visited yet. So we visit 1, and the discovery time of 1 would be okay. So I see I have done one mistake here. The discovery time of 3 is 5, so the discovery time of the 7 needed to be 6, because we visited 3 and then 7. So the discovery time of 1 would be 7, and we also initialize the earliest discovered node reachable to be 7. 1 has only one adjacent node, which is 2, and that happens to be its parent node. So we compute the minimum of the current earliest discovered node reachable and the discovery time of 2, which is 1. So we update the earliest discovered node reachable from 2 to be the node which has discovery time 1. So now the we have traversed all the um, descendants of 2, so we backtrack to 2, and now we would actually compute the earliest discovered node reachable from 2, and we see the minimum of the earliest discovered node reachable from all the adjacent nodes is actually 1. So the earliest discovered node reachable from 1 actually remains the same, and that makes sense because 2 is the start node of the DFS. So when I said that we compute the earliest discovered node reachable while backtracking, we need to keep in mind when I say backtrack and when I say compute the earliest discovered node reachable, we are computing the earliest discovered node reachable for the node from where we are backtracking, and not for the node where we are backtracking to, because we don't know if all the adjacent nodes for the nodes where we are backtracking to have been processed or not. So we compute the earliest discovered node reachable at the callback of the DFS for every node. So whenever we are backtracking, at that time we compute the earliest discovered node reachable and then backtrack. That is why when we backtracked from 4 to 2, we did not recomputed the earliest discovered node reachable from 2 because um, DFS for all the adjacent nodes for 2 was not completed because 1 was still left. So um, but we were backtracking from 4, so we recomputed the earliest discovered node reachable from 4, and then we backtracked to 2, and we saw we figured out if we have any unvisited node which are adjacent to 2, and we saw we had one, so we processed all the unvisited nodes, and then when we backtracked to 2, we recomputed the earliest discovered node for 1, and then when we backtracked to 2, we saw that all the adjacent nodes for 2 have been computed. So now we are recomputing the earliest discovered node reachable for 2 at the callback of the DFS. Now we backtrack from 6 to 5. 5 has 1, 2, and 3 adjacent edges. And out of the 3 adjacent nodes, which are 2, 4, and 6, 2 and 4 happens to be its ancestors. So I will take the minimum of the discovery time of 4, discovery time of 2, and the lowest the earliest discovered node reachable from 6. The earliest discovered node reachable from 6 is 3, discovery time of 2 is 1, discovery time of 4 is 2, so the minimum is 1. So for 5, I would put the the earliest discovered node reachable is the node with discovery time 1. And if you also look at the given undirected graph, you can actually reach the node 2 from node 5 using just one back edge. So using one back edge, 2 is indeed the earliest discovered node from 5. Now we backtrack to 4. For 4, we have 2 adjacent edges connecting to 2 and 5, out of which 2 happens to be its parent. So we will take the minimum of the discovery time of 2, which is 1, and the earliest discovered node reachable from 5, which is also 1. So we will and the current earliest discovered node reachable from 4 is 2, so the minimum of 1 and 2 is 1, so we update the earliest discovered node reachable to be 1. Now we backtrack to 2. 2 has 3 adjacent nodes, 5, 4, and 1, out of which one is not even on the call stack because we because we haven't visited 1 yet. So we have only 4 and 5. So when we backtrack to 2, we actually finish doing the DFS on 2. So to finish doing the DFS on 2, we actually need to visit the other adjacent node, which is 1, which is not visited yet. So we visit 1, and the discovery time of 1 would be okay. So I see I have done one mistake here. The discovery time of 3 is 5, so the discovery time of the 7 needed to be 6 because we visited 3 and then 7, so the discovery time of 1 would be 7. and we also initialize the earliest discovered node reachable to be 7. 1 has only one adjacent node, which is 2, and that happens to be its parent node. So we compute the minimum of the current earliest discovered node reachable and the discovery time of 2, which is 1. So we update the earliest discovered node reachable from 2 to be the node which has discovery time 1. So now the we have traversed all the um, descendants of 2, so we backtrack to 2, and now we would actually compute the earliest discovered node reachable from 2, and we see the minimum of the earliest discovered node reachable from all the adjacent nodes is actually 1. So the earliest discovered node reachable from 1 actually remains the same, and that makes sense because 2 is the start node of the DFS. So when I said that we compute the earliest discovered node reachable while backtracking, we need to keep in mind when I say backtrack and when I say compute the earliest discovered node reachable, we are computing the earliest discovered node reachable for the node from where we are backtracking, and not for the node where we are backtracking to, because we don't know if all the adjacent nodes for the nodes where we are backtracking to have been processed or not. So we compute the earliest discovered node reachable at the callback of the DFS for every node. So whenever we are backtracking, at that time we compute the earliest discovered node reachable and then backtrack. That is why when we backtracked from 4 to 2, we did not recomputed the earliest discovered node reachable from 2, because DFS for all the adjacent nodes for 2 was not completed because 1 was still left. So but we were backtracking from 4, so we recomputed the earliest discovered node reachable from 4, and then we backtracked to 2, and we saw we figured out if we have any unvisited node which are adjacent to 2, and we saw we had one, so we processed all the unvisited nodes, and then when we backtracked to 2, we recomputed the earliest discovered node for 1, and then when we backtracked to 2, we saw that all the adjacent nodes for 2 have been computed. So now we are recomputing the earliest discovered node reachable for 2 at the callback of the DFS. Now that we have computed the discovery time and the earliest discovered node reachable for all the nodes, how we actually determine whether a node is an articulation point or not. So for every node, we see what is the minimum of all the earliest discovered nodes reachable from all of its descendants, and then we take the minimum of that. So say we are at 6, and say, just imagine 3 and 7, say 3 is connected to 4 and 7 is connected to 2, and imagine that 2 has lower discovery time than 4, then we would know that 2 is the minimum earliest discovered node that is reachable from its descendants. So we know that even if the current node is removed, the rest of its descendants are connected to the rest of the graph, because they are connected to at least one node which was discovered before the current node was discovered, which means at least one of its descendants has a back edge. So we would compare the earliest discovered node reachable from all of its descendants, and we will take the minimum of that, and then we will see that whether that is greater than equal to the discovery time of the current node or not. It is very important to note here that we should not compare with the earliest discovered node reachable from the current node, and we know why. That is because we cannot have more than one back edge. So for every node we need to compare this minimum of earliest discovered node reachable from all descendants, whether that is greater than or equal to the discovery time of the current node. So if this holds true, that means that none of the descendants of the current node has any back edge that connects them back to a node that is discovered before the current node. So we can actually divide we can actually divide this whole graph into two parts around the current node. So like, say if the current node is 6, we can divide the DFS spanning tree into two parts by removing the current node. Now we get two parts here. This part is the ancestor part, and this part is the descendant part. So the removal of the current node will not impact the connectedness of the graph if these two parts are connected to each other. If the descendants are connected to the ancestors with one or more back edge, then even if we remove 6, the current node, the graph will not become disconnected, and that is exactly what we determine using this condition here. Before jumping on to the code, let me discuss one more very interesting scenario here, and which we will be using in the code to determine the articulation point, and that is very specific to the start node of the DFS. So let's take two different undirected graph like this. Say we have one, and then it connects to 2, then it connects to 3. This is one undirected graph, and then we have 1, this connects to 4, then now if we start, like, say for both the graphs we start the DFS from 1. So for this graph, the earliest reachable node for 1 will be 1, for 2 will be, so the discovery time of one will be 1, for 2 will be 2, and for 3 will be 3. This is the discovery time. And then if I also want to mention the lowest node reachable using just one back edge, then for 3 we see that the lowest node reachable is 2, and 2 has the discovery time 2, so I write 2. For 2 it will be 1, which has discovery time 1, and 1 will obviously have discovery time 1. And now let's take a look at this graph. 1 has discovery time 1 and the lowest reachable node as 1 as well. 4 has discovery say 4 has discovery time 2 and the lowest reachable node is 1. 2 has discovery time 3, the lowest reachable node is 1, which has discovery time 1. And 3 has discovery time 4, the lowest node that is reachable from 3 using one back edge is 2, which has discovery time as 3. Now we would see that for both the cases, the adjacent, the directly the immediate adjacent nodes of the starting root, so this is the start node of the DFS. So what we discussed, for any node, if we see for any of its descendants, the earliest discovered node reachable for any of the adjacent node, if that is greater than or equal to the discovery time of the current node, then we know that there is like the current node is an articulation point. So here when we are at 1, we see that it has only one adjacent node, which is 2, and 2 actually for 2 this condition holds true, because the 2 has the earliest discovered node reachable is 1, and 1 has the discovery time of 1, and 1 is indeed greater than or equal to 1, which makes 1 as the articulation point here, which is the same for the second graph as well. We see that for both 2 and 3, their earliest discovered node reachable is greater than or equal to the discovery time of 1, which makes 1 an articulation point in this graph as well. Now let's actually try to remove the 1 and let's see what happens. I am removing 1, I am removing the adjacent edges. So we actually get two disconnected components. So 1 was actually an articulation point. Now let's do the same thing for the other graph. Let's remove 1. Okay, the condition held true, which made 1 the articulation point, but I don't see any disconnected component here. We have one connected component here, so 1 was not an articulation point in this graph, which means there is something going on when a node is the start node of a DFS. So let me put the 1 back in the graph and let's see what is going on. In the second graph, we see that when when the start node of the DFS is actually an articulation point, there would be at least one adjacent node which is not connected to the other component which is connected through other adjacent node of the start node. So we have this component which is connected to the start node, which is 1, using the node 2, and we see that 4 is not connected to that component. If it were connected, then while we were doing DFS on this component, we would have discovered 4. But since 1 is an articulation point, we did not discover 4 from this component, which means if we do a DFS spanning tree, then in that spanning tree the root will have more than one direct child. Right? The spanning tree will be like this, and we have 1 and we have 2 children here. So for start node, we need to keep track of the child count. If child count is greater than 1, then start node is an articulation point. So after we have determined that a graph has one or more articulation points, what is the mitigation that we should take to make sure that the graph does not get disconnected after the removal of one or more articulation points? The answer is easy. You need to figure out the disconnected components you get after removal of the articulation points, and you need to make sure that those disconnected components are no more disconnected. So you need to connect those disconnected components with each other, at least using one edge. And you don't have to do this for every pair of disconnected components. You will have to make sure that you can go from any component to any other components using at least one edge. So let's see what I mean by this. So let's remove all the articulation points from the graph first. So we got 3 disconnected components here, and we need to make them connected. So we have one component which has only 1 in it, and this is another disconnected component, and this is another disconnected component. So we need to connect them, and we can do this by any way you want. Say we connected 7 and 4, and then say we connected 1 and 4. We can do this, or we can do any other way we want. We can connect 1 to 3 and 4 to 7. That way we know that we can go to any other nodes from all other nodes. And now let's bring back the articulation points. Yeah, so that is how we can avoid having the graph getting disconnected due to the removal of the articulation points. Before going to the coding section, let me show you how you can access the code for this topic and any additional content I add in the future. So go to the algorithms and the data structures link. Here you would find a lot of algorithms we have talked about earlier. Feel free to check those out. There are some really good algorithms with detailed explanations, with coding problems, which I think would be very beneficial if you are preparing for coding interviews or competitive programming, or if you are a student, a student, and you have tests or assignments, or preparing for the campus interviews. So from here you need to go to the articulation chapter here. Um, the link is the algorists.com/algo/graph/articulation point, and there you would be able to access this video, the accompanying code, and anything I add in the future. I would also add some really interesting coding problems related to articulation point as well, that would easily help you to master the concepts we just discussed. Also, if you want me to cover any specific algorithm or any specific topic, feel free to comment or reach out to me at admin at thealgorists.com, and I would make sure that I would make a tutorial and write a chapter here on the algorithms. Let's start coding. We will first code the DFS method. So, and we'll be using this, we'll be calling this method from the get articulation points method that we'll be working on after getting done with the DFS method. So it will be of type void and DFS. What are the parameters we need here? We definitely need we need to pass the graph. We will be representing the undirected graph as an adjacency list. So this will be a list of lists, because for each node we would be having a list of its adjacent nodes. So we will be having a list of the adjacent lists. We are representing each of the nodes with integer. So the list of the adjacent nodes will contain the ID for each of the adjacent nodes. Then we need to specify the current node that we are going to do the DFS on right now. So that will be integer ID of the current node. Then we need the a set to keep all the articulation points. So let's take a set here. I'm taking set because there should be no duplicates. So and set handles the duplicates on its own. Set has no duplicates in it. What else we need? We need to pass the data structure that is keeping sequence numbers for the nodes, and we also need to pass the data structure that is keeping the lowest reachable node for each of the nodes. So I can take an array for that. Sequence numbers. And we also need to pass the sequence number for the current node that we will be doing in the DFS on. We'll have to keep this in mind that array is zero-based indexed, but in our undirected graph, undirected by connected graph that we'll be passing, it will have the nodes starting from starting from 1 to n. So if there are say 8 nodes, the IDs of the nodes would be 1 to 8 and not 0 to 7. We need to keep that in mind while coding. So we while determining if our node is an articulation point, we look for two conditions. We see that if the node is a parent, and if okay, so also now I just remember that we also need to pass the parent array. So we are missing the parents here. One of the conditions is if the current node is a parent, then we need to see if the parent has more than one child in the DFS spanning tree that we are going to create. So definitely we need to keep a variable for the child count, and I will initialize that as 0. And the second condition, as we already discussed, is um, to see that the lowest reachable node for any of the adjacent nodes is greater than equal to the sequence number of the current node is or not. If it is, then the current node is an articulation point. So we are visiting the current node. So I just showed, which means we will have to pass one set for visited as well. You might be thinking that why I'm not taking a list here and here. That is because to search for an element in a list, it takes linear time, but in a hash set it is constant time in most of the time. The only exception is if there is a collision. So we can take a set for visited, or we can also take an boolean array for visited, and we can just mark the index as true whenever a node is visited. So visited current node -1, and this is very important. And as I said, array is zero-based indexed, but the node IDs are not, so we need to do current node -1 equal to true. We need to put the sequence number. Sequence number. We would be initializing the lowest reachable node as the sequence number of the current node as well, and then while we traverse its adjacent nodes, we will see if we are getting a lower reachable node or not. Okay, so now we would do a DFS on its adjacent children. I mean its adjacent nodes. Um, so we know how it works in DFS. We should not visit a node twice. So if a node is already visited, we should not do a DFS on that again. So we need to do a check whether the adjacent node has been visited or not. And if it is not, then we will do a DFS on that. And we also need to increment the child count for the current node. We need to assign the current node as the parent of the adjacent node. And then we need to do a DFS. So we would be passing the adjacent node here because we will be doing a DFS on the adjacent node. Adjacent points. We need to increment the sequence number by 1. Okay. So we do this. So now we will have to see if we can get a lower reachable node through the adjacent node or not. So if the node has a back edge to any of the earlier nodes, the nodes which have been already discovered in the DFS spanning tree, then we would get an earlier node which is visible from current node as well, because if a lower node is visible from a node's adjacent node, then that is also visible from that node through that adjacent node. But as we have already discussed, we cannot use more than one back edge, because if we have more than one back edge, then the node which connects those back edges, those nodes would act as single point of failure. So if we remove one of those nodes, the graph would become disconnected. So one of the adjacent nodes of the current node, if the node is not root, would be its parent. So the path which leads to its parent is already a back edge. So we cannot have any more back edge in that path, which means if the adjacent node is a parent, we should not take the lowest reachable node for the parent, because that might have one more back edge, like one or more back edge, and that would lead to having more than one back edges in that path that lead to the lower node, the earlier node, which we cannot have. So so we will be taking the minimum of the current lowest reachable node of the current node and the sequence number of the parent. So if the adjacent node is a parent, then we cannot take the the lowest reachable node for the parent, we need to take the sequence number for the parent. So if the adjacent node is the parent of the current node, then we take the minimum of the current the lowest visible node for the current node that we have gotten so far, and the sequence number of the adjacent node, which happens to be the parent. Else we would take the minimum of the lowest visible node found so far for the current node and the lowest visible node for the adjacent node. So now we will look for if the condition has been met for the current node to be an articulation point or not. So if the current node is parent, I mean if the current node is the root of the given graph, I mean the root of the DFS planning tree that we just formed. So if the current node is the root of the DFS planning tree we are creating, then we should check for the child count whether that is greater than 1 or not. If it is, then we have gotten an articulation point and the current node is the articulation point. The parent and the parents array is an integer array which is initialized with zeros, and the IDs of the nodes start from 1. So for all the nodes which are not root of the DFS spanning tree, they would have non-zero value as their parent, but the root would have 0 as its parent. So we will see if the current node is 0 and child count greater than 1. Or if the current node is not the root and the lowest reachable node from the adjacent node happens to be greater than or equal to the sequence number of the current node, then we know that we have gotten an articulation point. So we would add the current node in the articulation point set. Now one thing to remember here, like depending on what we are trying to achieve, we might need to do an early termination here. Like if we are trying to find if a graph has an articulation point or not, we can do an early termination here, and we can just return from here. But since here we are trying to compute all the articulation points, we should not do an early termination, and we should let the whole processing go through with the rest of the adjacent nodes as well, because our objective here is to find all the articulation points and not just one. Let's implement the get all articulation points method from where we will be calling the DFS method we just implemented. So it will be of type of set of type integer, um, and then get all articulation points, and we'll have to pass the biconnected graph. So we'll be passing the adjacency list. Here we need to take arrays for the sequence numbers, the lowest node reachable for each nodes, and we need to take an array for parent. So we need to know the size of these arrays. So the size would be, the length of these arrays would be equal to the total number of nodes we have. We can easily get that from the adjacency list because the number of nodes will be equal to the length of the adjacency list. So now we'll be taking an arrays for the first array I'm taking is for the sequence numbers. The second array we need is the lowest, I would say earliest discover node reachable, and then we need an array for the parents to keep the parents. And then we need a set to keep the articulation points. We will be taking a hash set. So for each node, we will be doing a DFS if the node is not already visited. So yeah, we also need for visited. We also need an array for the visited. And let's see. We have taken the visited sequence number, visited node. Just one thing. I need to maybe put this method on top of the DFS handling method so that I can see in which order we have the parameters in the DFS method. So I'm just iterating about all the nodes so that I can do DFS on them. So as I said, the node starts with 1, and if there are n number of nodes, so we would have the nodes as from 1 to n. If we have not visited the node, then we will do a DFS on that. I will be the current node, then it is in the articulation points and set sequence numbers. We'll be sending them and then we'll be passing the parents array. So we can start the sequence number from anywhere we want. I will start the sequence number from 0 and then visitor. And then we will return the articulation points. So this is the complete code for the articulation points. So now we will be doing the testing to see if our code has any bugs or not, or if we are getting the expected result. So for I have already constructed a graph, a connected graph for testing. So I'll be just pasting the code for that here. Copied the code that I had ready for the testing, where I have already created the graph, that the undirected graph that we will be testing on. So let me paste. Yeah, so this is the bi-connected graph that we'll be testing on. And as you can see, if we remove 3, then we will have to disconnected component. In one component we will have 1 and 2, and the other component we would have 4, 7, 5 and 6. The same applies for 4 and 7 as well. If we remove 4, we would have two different, two disconnected graphs. If we remove 7 from the graph, then we would have 2 disconnected graphs again. So 3, 4 and 7 are the articulation points here. So I have the graph ready here. So let me call the get all articulation points method, and let's see if we are getting 3, 4 and 7 or not. Alright, let's run the program and let's see. Let's keep our finger crossed. Okay, so we are getting an error, an exception here. We are getting array index out of bounds exception. So my guess would be somewhere we forgot to do -1. Let's see. Line number 67. So here, yeah, I see here we need to do a -1, and I can see here as well. Okay, it should be fine now because I don't see anything else. Only that exception there. So let's run now. Okay, yeah. We got 3, we got 4, we got 7. Great. So our implementation is correct and it works as expected. That's great. We'll see you in our next video. Till then, take care and stay safe.